All right, greetings everyone. Welcome to the first part of the video for section 4.2. So in 4.1 we talked about exponential functions. Here in section 4.2 we'll now start looking at the graphs of exponential functions. So on that note, what we're going to do is we're going to start by graphing some stuff. So I'm going to go to my graphing calculator here. And I'm going to go to my graphing utility here, and I'm going to start by graphing the function 3 to the x, which I know is a specific exponential function, but we're going to look at the graph of this function to try to tease out some of the general characteristics of an exponential function. So when I graph this, notice I get a shape that looks something like that. I know it's kind of hard to see. Let me try to highlight it a little bit more. So it's this shape here. Okay. And let's identify some of the important features of this. So first of all, the vertical intercept. So where the function intersects the vertical axis, we'll notice that happens right here at the point, looks like it's 0, 1. Okay. Sorry, trying to write that legibly. There we go. And then you may also be able to tell that this function has a horizontal asymptote. So it actually has no horizontal intercepts, but it does have a horizontal asymptote. And do we see where that is? Yeah, it looks like it's right along the horizontal axis here. And so as we've talked about with rational functions, the equation for that is just, it's a constant function along at the value 0. So we could say that our horizontal asymptote here, the equation of it, because it's a line, I could say something like g of x equals 0. And then let's look at the long run behavior here, because this is kind of interesting. So as x goes towards positive infinity, so as the input values go to the right, okay, notice what the output values do. They go up and up and up. So it looks like as x goes to positive infinity, we'll call them f of x here goes towards positive infinity. But then as x goes towards negative infinity, okay, so now going the other way, look, notice that instead of going towards positive or negative infinity, the output values are getting closer and closer to that horizontal asymptote at that value at 0. So what we see is that our f of x's, or our outputs, are getting closer and closer to 0. So this is, I think, the first instance we've seen where in one direction the long run behavior goes towards some sort of infinity, but in the other one it goes towards a specific number. Okay? All right, and then also looking at the concavity of this function. So notice that it is concave up, right? We see that up like a cup shape. Okay, so it's concave up there. And then I also want to look at the domain and range of the function. So the domain would be the set of all possible input values. Well, it looks like we can go as far left or as far right as we want. So our domain here would be negative infinity to positive infinity. Our range, though, well, what's the lowest input value, or sorry, output value we can hit? Well, we have that horizontal asymptote, recall, along the horizontal axis. And that's about as low as the output values can get. In fact, they never actually get to that value, right? They get really, really close but never get there. So our range starts at 0, but not including 0. Then as we also saw just a minute ago, the function shoots up here. So it looks like our output values get closer and closer to positive infinity. So our range is 0 to positive infinity. All right, so then we want to look at what sorts of changes happen if we start to change some things about this function. So first of all, let's remind ourselves that this function we're looking at here, this blue one, is f of x equals 3 to the x. Now I'm going to go back to my graphing utility, or to my place where I enter graphs. I'm going to add a second function here. And this one is going to be 2 times 3 to the x power. Let's graph that. So notice that'll come out in red. And what do we notice? Well, still has the same horizontal asymptote, right? So it's still getting closer and closer to the horizontal axis. The long run behavior looks to be about the same, as does the domain and range. But what has changed? Well, it looks like the only thing that has changed is that vertical intercept, right? And now the vertical intercept for this new function is at 0, 2. And recall that the function formula was f of x equals 2 times 3 to the x. And notice the value that is being multiplied out front is the one that ended up being the output coordinate of the vertical intercept. I wonder if that's related somehow. All right, let's look at another variation on a exponential function. In this case now we're going to make this negative 2 times 3 to the x. All right, I'll graph that. So again, there's our function, and then the negative 2 times 3 to the x, boom. All right, notice what has happened here. So first of all, so this is, call this h of x equals negative 2 times 3 to the x. Well, notice now this function has reflected over the horizontal axis. And in reflecting, it is now actually concave down, right? So its concavity is facing down now rather than up. The domain is still the same. It's still negative infinity to positive infinity. However, the range has changed now, right, for this function. So the range for this function is now negative infinity up to 0 because all of the output values are negative. Horizontal asymptote is still the same. Long run behavior has changed a little bit, right? So as we go towards negative infinity, we're still going towards 0. But as we go towards positive infinity, we're actually going towards negative infinity now. And what was the other thing I wanted to point out here? Oh, the vertical intercept. Notice that now the vertical intercept for this function is at the point 0, negative 2. Which again, we see that negative 2 is our output value, which is also that leading coefficient there. Starting to see some patterns there. All right, and then one more form I want to compare this to. Let's look at what happens now if we graph just 1/3 to the x. How that differs. So there's our 3 to the x, and there's the 1/3 to the x. And what do we notice happened? Well, it looks like there was some sort of reflection across the vertical axis. So that's something to note. Also, notice that our original function, f of x equals 3 to the x, notice that it increases from left to right. Right? So as we go from left to right, the output values are going up. But what happens with the other function as we go left to right? Yeah, that's right. It goes down, so it's actually decreasing. And notice that one of the big differences between these two functions is the number being raised to the power, right? So here we have 1/3 being raised to the x power, and here to the 3 being raised to the x power. Notice that in the blue one, the f of x equals 3 to the x, that value being raised to the power is greater than 1, and that's when the function was increasing. And in the second one there on the left, the value being raised to the exponent is less than 1, and now the function is decreasing. Okay, so that's just doing some analysis of the graphs of exponential functions. So let's go back to our PowerPoint. and look at a slide that has basically a summary of this information. So if we have a function given in the form f of x equals a times b to the x, and I want you to notice, first of all, that's just a times b to the x. There's nothing being added at the end. So there's something being added at the end. All this, some of this information below changes. But if we have that form, a times b to the x, here are some of the properties we'll see. So firstly, a is the vertical intercept of the graph, meaning that the graph will intersect the vertical axis at the point 0a. The value b, the value being raised to the exponent, determines the rate at which the graph grows. So it increases if that value of b is greater than 1, so that's what we saw with 3 to the x. And it decreases if that value is between 0 and 1. Okay, so like when we had the 1/3 to the x. Notice that we only have b greater than 1 or b between 0 and 1. We do not have b less than 0. Do you remember why that is? Right, that's because the value for b can never be negative. That's from section 4.1. We also have the graph will have a horizontal asymptote at, they say y equals 0, but it's really, g of x equals 0, h of x, it's some constant function where the output is constantly 0. The graph is concave up if that value for a is greater than 0, concave down if it's less than 0, we saw that. And additionally, the domain of the function is all real numbers, and then the range is 0 to infinity. Okay, so those are some of the basics of graphs of exponential functions. All right, that's all for now. Thank you for watching.